Welcome to this lesson on half-life calculations. The key terms we need to know are half-life, random, radioactive decay, count rate, and unstable isotope. Before we start, I'd like you to write down 4 types of radioactive decay and state what is meant by half-life. And then consider how can you work out the amount of radioactive material that will be around in 1,000 years if we haven't even known about radioactive materials for more than 200 years to observe the decay? Pause the video to answer these questions and consider your answer. Half-life is the time taken for half the number of radioactive atoms in a sample to decay. Random means something that cannot be predicted. So for instance, rolling a dice, you can't predict where it'll land. And also an unstable isotope, exactly when it will decay cannot be predicted. So it is called random. Radioactive decay is when an unstable nucleus emits radiation to become more stable. Count rate is the number of particles of ionizing radiation that reach a detector per second. This is measured in becquerels. And an unstable isotope is an atom that is likely to radioactively decay. So, we have an equation that we can use to calculate what the mass of an isotope will be if we know the number of half-lives that have happened. Now, note, you do not need to remember this equation, and in fact, you can work this out intuitively for most calculations you'll need to use. So you will not actually ever have to use this equation, but for those of you who are good with maths, you can use this equation. So the mass of an isotope equals the initial mass of the isotope divided by 2 to the power of n. And when we say to the power of n, what we mean is the number of half-lives. So if 1 half-life has passed, we'll divide the initial mass of the isotope by 2. If 2 half-lives have passed, we'll divide the initial mass of the isotope by 2, and then we'll divide it by 2 a second time, because it'll be 2 squared. And similarly, if there are 3 half-lives that have passed, we will divide it by 2, and then we'll divide it by 2 again, and then we'll divide it by 2 again, because this is 2 to the power of 3, because the 3 half-lives have passed. Now that is a little difficult to get your head around, and so we will be doing some example calculations to help you. This is another version of the same equation. Again, you don't need to remember this, and you can work it out intuitively, but instead of mass, we're looking at the count rate. So that means how many particles of ionizing radiation it's emitting per second. Okay, let's take a look at our first calculation. So calculating the mass of isotope left. So cobalt-60 has a half-life of 5.27 years. An initial sample of 0.1 kilograms of pure cobalt-60 is stored at a nuclear facility. Calculate the amount of cobalt-60 that will be left in 26.35 years. So the first thing we do, as always, is write down what we know. We know the half-life is 5.27 years. We know the initial mass is 0.1 kilograms, and we know the time that we've been given is 26.35 years. So for step 2, the question is, how many half-lives have that been? How many times will we have to divide the initial mass by 2? So the number of half-lives is 26.35 years divided by 5.27, where 5.27 is the half-life. So the number of half-lives is 5. We've halved that number 5 times. So what we can do next is you can choose. You can use that equation, final mass equals initial mass divided by 2 to the power of 5, or you can just take that initial mass in your calculator and divide it by 2 5 times in a row. This will give us an answer for the final mass of 0.003125 kilograms. So all we've done there is we've taken that initial number and divided it by 2 5 times in a row. Now, one mistake a lot of people make is to accidentally divide it by 10. So they'll do 2 times 5 because I think, oh, 5 half-lives, so we'll do 2 times 5, which is 10, and then divide it by 10. No, that would give you the wrong answer. You've got to divide it by 2 because it's halving 5 times in a row. So this time we're going to calculate the count rate rather than the mass of the sample after a certain amount of time. Now remember to copy these steps down into your books and to write notes. Polonium-210 has a half-life of 138 days. An initial sample of polonium-210 emits 2,200 becquerels. Calculate the count rate of polonium-210 after 414 days. So, as always, our first step is to write down what we know. We know that the half-life is 138 days. The count rate is 2,200 becquerels at the start, and we have the time of 414 days in total. So what we need to do is to figure out how many half-lives that has been. So we take the 414 days in total and divide it by how long a half-life is. So we find that there have been 3 half-lives. That means we're going to be taking that number, 2,200, and we're going to halve it 3 times. So you can either do that with the equation, count rate equals initial count rate divided by 2 to the power of 3, or you can simply put the initial count rate in your calculator and divide it by 2 3 times in a row. This will give us an answer of 275 becquerels. Okay, in this one I'm only going to give you some of the steps and you'll need to complete it yourselves. So copy down the steps I show you and then complete them in your book. So polonium-218 has a half-life of 3 minutes. An initial sample of 512 grams of pure polonium-218 is stored at a nuclear facility. Calculate the amount of polonium-218 that will be left in a quarter of an hour. So let's write down what we know. First of all, half-life is 3 minutes. Second of all, the mass is 0.512 kilograms. And finally, the time that it took, quarter of an hour, is 15 minutes. So our next step is to find out the number of half-lives that have passed. In this case, we've got 15 minutes divided by how long it takes for a half-life, which is 3 minutes. That gives us 5 half-lives. Your job now is to complete this calculation. Pause the video now to complete the steps that are missing. Calculating count rate. So this time technetium-99 has a half-life of 6 hours. An initial sample of technetium-99 emits 1,280 becquerels. Calculate the count rate of technetium after 1 day. So, firstly, we write down everything we know. We know that the half-life is 6 hours, and we know that the count rate is 1,280 becquerels, and we've had an entire day. So we need to work out how many half-lives it has been. So the number of half-lives is 24 hours divided by the 6 hours for the half-life. That gives us that there has been 4 half-lives in this time. Finally, complete the last 2 steps yourselves. Make sure you write out all the steps clearly in your notes. Now I'm going to give you 2 more extreme examples, some unusual ones. A sample of tritium, in other words hydrogen-3, starts with an initial mass of 32 grams. After 24 years there is only 8 grams remaining. Calculate the half-life of tritium. So this time we're looking for the half-life. So we write down what we know. The initial mass is 0.032 kilograms. The final mass is 0.008 kilograms. And the time is 24 years. So what we need to do with this is to find out how many times you've had to halve the 0.032. So how many times do you have to halve 32 grams before you'll get to 8? So first of all, we divide it by 2, and that gives us 16. And then we divide it by 2 again, and that gives us 8. So we've had to halve it twice. So that means there has been 2 half-lives. So 24 years is 2 half-lives, and therefore a half-life must be 12 years long. And now for the most challenging question that I'll show you how to do. You are unlikely to get a question this difficult in your exam, but it's useful to be able to understand for those people that like the equation version. This will help you understand what you do when it's not an exact number of half-lives. So cesium-137 has a half-life of 30 years. The initial sample of 256 grams of cesium-137 is stored at a nuclear facility. Calculate the amount of cesium-137 that will be left in 15 years. Okay, so first of all, we write down what we know. We know the half-life is 30 years, we know the initial mass is 0.256 kilograms, and we know that the time we've had is only 15 years. So we haven't actually had an entire half-life. So the number of half-lives, 15 divided by 30, which is 0.5. It's only been half of a half-life. So we cannot do the divide by 2 system. We have to use the equation this time. So the final mass equals the initial mass divided by 2 to the power of the number of half-lives. Well, the number of half-lives is 0.5. So what we can do is we can take 256 divided by 2 to the power of 0.5, and that gives us 0.181 kilograms. Sorry, that 256 was in grams, so it's 0.256 divided by 2 to the power of 0.5. Now, as I said, that is unlikely to come up in your exams. I've not seen that. I think it's likely to be too complicated to come up in the exams, but it's useful to those of you who do like the equation to have a better, more full understanding of the process. Okay, and finally, 3 questions for you to complete yourselves. Follow the steps that I have taken each time and write these out clearly in your books. Let me know when you're ready to receive the answers to these questions.